The tape cut out, or I guess I should say the camera shut off when we were making the previous video, part 2. So I'm going to pick up sort of where we left off. In that video, what we were doing is we were making all possible comparisons among 3 treatment groups. So we had unfertilized plants and plants fertilized with 2 different fertilizers. So as I explained in the previous video, usually people will approach this type of problem using a Tukey's test. But it is possible to analyze the data using a t-test. Now, again, the null hypothesis we're working with is that all the population means are the same, and we're making all possible comparisons among them. So what that means is that we're going to make this comparison. We're going to compare fertilizer 2 and the unfertilized group. The null hypothesis is that the difference between those is 0. These are all differences between means. So there's 3 possible comparisons that we're going to be making. Okay, so let's look over here, and in this panel I show the comparison between the fertilized plants and the unfertilized plants. So I think you can still see that the fertilized plants had a mean of 12 and the unfertilized plants had a mean of 8. All right? Now the null hypothesis is that the populations are equal. All right? So here we have a t-statistic. Now this is just like an independence groups test. In fact, you do exactly the same thing. The only difference is that we're going to adjust the probability. And that is necessary because we're using the same sets of data multiple times. So for example, we're using the data for calculating the fertilized, the second fertilizer twice. We're going to use that data to compare to the unfertilized data, but we're also going to use that data to compare to the other fertilizer. So because you're using the same data set multiple times, it inflates alpha. Okay, so here we have the formula that we're using for a t-statistic. Now this is the same formula you've seen before. Now let me tell you what the most common mistake is I see when students analyze something like this. Now this really can occur when you're doing a Tukey's test and a Bonferonni corrected t-test on the same data. All right? So you see the MSE term here? This is not the same mean squares error that we used in the Tukey statistic. So remember, in the Tukey statistic, we were taking all 3 variances and taking an average of them. When you're doing a Bonferonni corrected t-test, you don't do that. Again, you work it just as though it were an independent groups test. So notice we only put the 2 variances for the groups we're interested in. This is a variance for the fertilized plants using fertilizer 2, and that is the variance for the unfertilized plants. Okay. Now when I plug all this in, so we've got the mean of the fertilized plants, the mean of the unfertilized plants, hypothesized difference is 0, right? When I plug all this in, I get 4 over the square root of 2.1, and then this is the t-statistic that I got, okay? What about degrees of freedom? Again, just like with the independence groups test. Notice we only look at the 2 groups for each calculation. So we had 40 plants involved in the calculation of this t-statistic, minus the 2 variances, 2 degrees of freedom for the 2 variances we're using, and that gives us 38 degrees of freedom. Okay. Now at this point we can look up the probability, and I will move you guys over here to the computer screen. All right. So let me first find this. Give me just a second here. Here we have the t statistic calculation. All right. So as you can see, I put in the t statistic that I calculated. Here's the degrees of freedom, and here's the probability. Now the thing is, that's the probability you would report if you were only comparing the two groups. But we're going to make all possible comparisons, so we have to adjust that probability by multiplying it times the number of comparisons we're actually making. So I've done that in the calculator here. Let's see, hold on, actually no. Let me do that. Okay. That is the probability that we got from Lane, all right? Now we're making 3 comparisons total. Fertilizer 1 times fertilizer 2. Fertilizer 2 times the unfertilized plot. And fertilizer 1 times the unfertilized plot. All right? Since we're making 3 comparisons total, this is too low, right? Because that would be the probability if we were only making 1 comparison. So to correct this, we multiply by the number of comparisons we're making. All right? And that gives us the probability that we're going to actually report. So how do we report this result? Let's come over here. All right. Notice we got a significant result this time because that probability is less than 5%. So we would say plants grew taller when treated with fertilizer 2. I'll point out one thing about this statement that we haven't really talked about before. Notice that this tells us the direction. In other words, you don't want to say something vague like the plants that are fertilized are different than the unfertilized plants, or even worse, we got a statistically significant difference. Don't say that. Just make a plain statement here, and then report your statistic and probability in parentheses. So you don't ever want to say they're statistically significant, because that would be redundant since we have a probability here. There's no need to bang people over the head with this information. All right, so you write the statistic with the subscript showing the sample size in the 2 groups. There's the t statistic that we got by using the formula. And then here is the corrected probability. So what I usually do, just to tell people that I've corrected the probability, is I'll put Bonferonni in a subscript to to P, and that conveys that information. Okay, so what we're going to do now is we're going to talk about testing assumptions. You can only do this when you have all the data. So I have uploaded some data here. We're going to rearrange everything. Let's see if I can do this before the computer cuts out on me again. Or the camera cuts out on me again. Just a minute. I readjust a lot of things here. All right, so when you're looking in D2L, you're going to see that I've put a new set of data in there. This is data taken from some lizards in a genus called Dendrogama. All right, so let's see here. Let me show you where some of these things are real quick. So here we have, this module in D2L. This is the new data set, Dendrogama interspecific comparisons. Okay, so if you download that, this is what it's going to look like. All right, so notice I've got 3 different species in here. And what we're going to do is we're going to compare each one of these species for the count of ventrals. So you can select the data in the ventrals. We're going to paste it into past. You guys have already done a lot of this, so I assume you remember how to do it. It's a good idea to always label your columns. Remember, you select column attributes so that you can keep track of what's what. Notice I've got the 3 species. That's Diadema, Australis, and Boulangerie. All right, and then I've pasted in all the data. Notice the sample sizes are different. So this is not something that you would know how to do by hand. As I said, we're going to use pass when we have unequal sample sizes. Now, Lane has some calculators that'll do these types of analyses. However, we've had a lot of difficulty getting them to work. So we're going to just use pass for this type of analysis. Okay, so let me show you a few things we can do with this. So first what we're going to do is we're going to select all 3 groups here. All right, now first I'm going to do a Tukey's test. So you go up here, you select univariate. Let me make sure you can see all this. Hold on, we're going to get the camera a little closer. And it looks like it needs to go up a bit. Hold on just a minute. That's the wrong thing. Okay, hopefully you can see that clearly. All right, so we're going to select univariate, and then we want to select ANOVA several sample tests. Okay, click on the first one here. Okay, so here we have, notice there's Tukey's pairwise. You see that? So we'll select that. This gives us the results of the Tukey's test. So notice what it says here in the little dialog box. It tells us that these numbers down here are the statistic, and then these numbers up here are the probabilities. So you would say Q equals 4.695, for example, if you were reporting the comparison between Australis and Diadema. Then you can look and see if it's significant. So notice here we have Diadema, here's Australis. That's the probability that goes along with that. Notice how it's highlighted, so it's clearly significant. Okay, so you can use pass to generate Tukey's statistics and probabilities. Okay, now what about these assumptions? All right, let's go back to that first thing. This was the first screen that popped up. If you need to get back there, you just click on the very first tab. Now notice here we have something called Levene's test for homogeneity of variance. Notice the probability is 0.187. So for this type of test, the null hypothesis is that all the population variances are equal. As long as this is above 0.05, we have satisfied the assumption. Now you can't say the population variances are equal, but you can say we satisfied the assumption of homogeneity of variance, and we can report that probability. Okay. Now, the other assumption of the Tukey's test is normality. Now, to get normality, I think we may have done that before in this class, but just in case you forgot or we never did it, we'll take a look at how to do that. So you select the groups you're interested in, and then go up here. Notice that under univariate, we have normality test right there. Click on normality test. Okay, so here there's a variety of different normality tests, but the one that everybody uses is Shapiro-Wilks. And so for Shapiro-Wilks, notice this time it gives us a statistic, the W, and a probability. So you can report both. Notice this one also gives sample sizes. So one way to report this would be, notice none of these things are less than 0.05, although Diadema is close. But for each one, we have satisfied the assumption of normality. So I could say something like, the ventrals of Diadema satisfy the assumption of normality, and then put in parentheses W equals 0.914, comma, P equals 0.077. Okay?
That's how you report whether or not you have satisfied this assumption. Okay, now remember that with t-statistics, you also have the same assumptions. So let's say we just were interested in these two. All right, so Diadema and Australis. To do a t-test on this, we go to two sample tests, F and T, so select that one. Notice that this gives us a t-statistic. There's a probability, as you can see, they're very different. That's the same result we got using the Tukey comparison. And then this is where we test for homogeneity of variance. So click F for homogeneity of variance. All right. So there is F. All right. That's the statistic that is used for this type of test. And notice this says P, same variance. What the same variance is there, that's actually what the null hypothesis is. The null hypothesis is that the population variance of Diadema and the population variance of Australis is equal. All right? We haven't violated this assumption. So again, you could say, I have satisfied the assumption of homogeneity of variance for Diadema and Australis. And then in parentheses, you would put this F value and this P value. Now you could use this same approach if you're doing a Bonferonni corrected t-test. Let's look at this again. So there's the probability of an independent group's t-test. Now if we decided to do Bonferonni corrected t-tests for those three species, and we made all possible comparisons, in other words 3 comparisons, we would need to multiply this by 3. If we only compared 2 of them, like what if we were only interested in Diadema and Australis and Diadema versus Boulangerie? And in other words, the one we didn't do was Australis and Boulangerie. If we only made 2 comparisons, then we would multiply probabilities by 2 instead of 3. Okay, now finally, let's see. I guess normalities, same approach there. You go here and you select normality test, and hold on, something's wrong. Let me try. Oh, I didn't select everything. So again, let's say we're just doing these two, univariate, normality. You know, there's the Shapiro-Wilks test. This should be the exact same result because it's the same data that we had in the previous one. All right, so forget about all these other tests of normality. Just focus on Shapiro-Wilks. That's the one most people use, and that's the one we're going to use in class. All right, so this concludes our little session on testing assumptions. Ordinarily, you know, there are alternatives if you violate the assumptions. So, for example, with t-test, univariate, let's see here, 2 sample tests, all right? What if you violated the assumption of homogeneity of variance? Notice there is an unequal variance t that can be used. Or if you violated one of these assumptions for Tukey's test. I'll just show you this, although we don't really do it in this class. Let's see, ANOVA, several sample tests, Tukey test. So let's say we had violated Levine's test. In this case, we haven't, but if we had violated Levine's test, there's this alternative over here called the Mann-Whitney pairwise test. And that's beyond, or using this is beyond the scope of this course, so we won't worry about that for now. But there is an alternative. Okay, so that concludes this video.